sincere thanks to the organizers for giving me an opportunity to introduce our recent work on the heterogeneous deoxydehydration (DODH) catalyst. Uh, uh, this is the first time to attend the now meeting. I really enjoyed the meeting and this progress. Okay, let's just start the presentation. The contents of my software is here, and the oxidation reaction is not so popular. This is a reaction equations. The PCNAL, which groups can be converted to double bond using the sort of catalyst and the sort of reductant. At first, I would like to explain the biomass-derived chemicals, production of the biomass-derived chemicals, and then I would like to explain the DODH and the DODH catalyst. This section is mainly focusing on our catalyst, linear, metal modified serial catalyst. And then we are talking about the linear serial plus the nickel serial, the physical mixed catalyst. We are also studying the molybdenum DODH catalyst, but I would like to focus on the rhenium DODH catalyst in this lecture. Okay. This slide shows the composition of the feedstock and the target products and the building blocks in the biomass refineries. This axis represents the oxygen carbon ratio and hydrogen carbon ratio. These are the fossil fuels, coal, crude oil, and natural gas. As you can see, the oxygen content of these fossil fuels are so low. On the other hand, in the case of the biomass, the oxygen content are so high, like the case of the cellulose and so on. Therefore, the target products, in this case, the diols are plotted here. For the production of the diols, if it will be used petroleum, because of the low oxygen content, the target products can be produced by the oxidation with the air or the hydration. The oxygen insertion is very important for making the target products. On the other hand, the biomass has a very high oxygen content. Therefore, the reduction is more important and reasonable reductant. One of the reasonable reductant is hydrogen. Recently, therefore, the CO hydrogenolysis, hydrodeoxygenations, and the deoxydehydration, in particular with the hydrogen as a reductant, more important reaction to decrease oxygen content. These are the platform chemicals in the biomass refinery proposed by the US DOE. You can see, these kind of compounds are over functionalized. Therefore, for the production of the diols, the reaction should be the defunctionalization. As you can see, the ethylene, propylene, the benzene, these are the platforms in the petroleum refineries. In this case, the functionalization is important. These are the completely different in the petroleum refinery and biomass refineries. Platform chemicals and biomass refineries are over-functionalized. Therefore, the selective removal of functional group is so important, and the development selective catalysts the reaction, for example, the new reaction is required. These are the building blocks in the biomass refinery. These compounds are shown on the basis of the carbon numbers. You can see the C4 building blocks is so limited, and it is not easy to functionalize have at the second positions. Recently, therefore, we proposed the potential another C4 building blocks is acetol. Acetol has been produced by the fermentation of the crude glycerol. The yield is not so low. Therefore, we are thinking that the acetol is a highly potential C4 building blocks. We are developing the catalyst for the CO hydrogenolysis. Iridium silica, rhodium molybdenum silica, and recently we are developing the iridium radium is supported on the rutile and platinum tungsten catalyst. Today, we are focusing on the deoxydehydrations. We are developing this kind of catalyst, the rhenium supported on celia modified with the metal particles. For example, the gold, silver, palladium metals. The important difference is the solvents. Reductant is all hydrogen in most cases, but the solvent, water is used for these reactions. Water is very good solvent for these reactions. On the other hand, water is not good solvent, and the ethers, alcohols, and alcohols, in particular the monoalcohols, the hydrocarbons can be used for this reaction. But water is not suitable for this reaction. We propose the active site is this kind of the monomeric rhenium species supported also. This is an example of our studies on the selective production of the C4 chemicals from acetol and 1,4-anhydroacetol. 1,4-anhydroacetol is easily produced by a simple dehydration of the acetol. These are the building blocks, and two kinds of reaction applies. Two kinds of reaction applied to these substrates. A variety of chemicals can be produced. For example, the deoxydehydration reaction plus hydrogenation gives the 1,2 butane diol very high yield, and for example, the monoalcohols, diols, butadiene, tetrahydrofran, dihydrofran, 1,4-butane diol, so on. Next, I would like to explain the deoxydehydration and the catalyst. This slide shows the proposed catalytic cycle of homogeneous rhenium catalyst. The reaction mechanism is not so complicated. Very simple redox cycle between the rhenium 7 plus and the rhenium 5 plus. The rhenium 7 plus is here. The rhenium 7 plus is reduced to the rhenium 5 plus by using the suitable inductor. For example, the and so on. And the diorate is formed, and the reaction of the diorate proceed to give the cis-double bond products. Basically, this reaction is almost the same. The reductant is a little different. The secondary alcohol is used for these reactions. Our target is development of heterogeneous deoxydehydration catalyst with hydrogen as a reductant. Generally speaking, the homogeneous DODH catalyst is not suitable, not good at the hydrogen activation. Our approach is a combination of the high valent radium species fixed on the oxide surfaces and novel methods with high hydrogen activation abilities. These are the example of the previous reports on the DODH catalyst. These are the homogeneous catalyst and the heterogeneous catalyst. This is a reaction equations. Usually, the homogeneous catalyst contain high valent rhenium, molybdenum, vanadium catalyst. Rhenium is here, molybdenum is here, the vanadium is here. The reductant is what is the secondary alphols and propylene protein and so on. And this is pioneering work of the development of heterogeneous catalyst. Rhenium species supported on the carbon materials, the reductant is hydrogen. But the disadvantage is that activity is not so high. This is a report by the Professor Gentoft. She is one of the organizers in this conference. But this is a pioneering work, but the activity is not so high. The reported heterogeneous catalyst shows lower electric activity than homogeneous catalyst. As you know, the heterogeneous catalysts have advantage in the catalyst separation and reusability. And hydrogen is one of the cheapest and the clean reductants. Development of the heterogeneous DODH catalyst with a higher catalytic performance and H2 reductant. Professor Gentoft wrote recently a very comprehensive review in the catalyst science technologies. This is a list of the high reductant in the DODH catalyst. This review covers all the aspects of the DODH studies. This is one of the examples, and a lot of various types of the reductants have been used for these reactions. Our study is focusing on the utilization of the hydrogen here. The advantage of the hydrogen is very cheap and industrially feasible. And on the other hand, disadvantage is hydrogen. Hydrogen is usually necessary, and the hydrogenation of the CC double bond DOD in the DODH products. Another important report is active species on the DODH catalyst, which is also reported by Gentoft. C is proposing that the leaching rhenium species are active. In the case of the rhenium titania, rhenium titania, rhenium silica, rhenium carbon, and so on. This figure shows the relation between the leaching amount of the rhenium species and the activity of the DODH reactions. On the other hand, in our case, the celia is a used sample. The rhenium celia was not mentioned in this work. We believe that rhenium species on the celia catalyst is the active species. Okay. We would like to introduce our work, rhenium catalyst with its reductant, the typical catalyst, the rhenium OX metal modified celia catalyst. Our experiments is conducted using this kind of reactor. The experiment is so simple. The catalysts are prepared by using sequential impregnations. And generally, we use a Celia support, and the commercial Celia is calcined at 870 Kelvin, and the sub-BT surface area is 80 square meter per gram. I think Celia, our Celia is not so special. The important point is the solvent, usually the camphor dioxane is used as a solvent. Sorry. This is the result of the 1-for-1 hydrolysis reactions, effects of the support for rhenium palladium catalyst. As you can see, cereals showed very higher activity than other support oxide. At this temperature, generally the little lower temperature than the usual case and the homogeneous case. Even at low temperature, palladium, rhenium palladium ceria showed very high activity, and the selectivity is also very high. The main product is a THF level. Another important point is the monometallic rhenium ceria also no activity. Monometallic palladium ceria almost no reactivity. The synergy of the rhenium ceria and palladium ceria generated very high activity. Next, I would like to show you the experience results of the highly active rhenium palladium ceria and the rhenium palladium silica with very low catalytic activities. In the case of the highly active rhenium palladium ceria, rhenium 4+ species and rhenium 6+ species, 4+ and 6+, was observed. On the other hand, rhenium palladium silica with a slow catalytic activities, rhenium 0 and rhenium 4+ observed. From these comparisons, it is concluded that ceria maintained the high valence of rhenium species by suppression of the deep reduction, for example, the rhenium metal and so on, even at the very high pressure of hydrogen, even in the presence of the palladium species. And another important point is the distribution of the valence of the rhenium. According to these results, we are thinking that the redox cycle between the rhenium 4+ and rhenium 6+ is suggested. This is the result of the 1-for-1 hydrolysis reaction using the rhenium palladium ceria, conversion and the selectivity as a function of the reaction time. 99% yield here is achieved and very high catalytic activities. We adjust the reaction temperature. The homogeneous catalyst data is shown here, and the heterogeneous catalyst shown here. And the frequency per rhenium atoms, the clearly higher than the case of the homogeneous catalyst. Another important behavior is the effect of the loading amount of rhenium. Conversion and selectivity as a function of the loading amount of rhenium. 0.5 and 2 activity is increased with increasing the loading amount. The activity is almost proportional to the rhenium. But you can find 4 weight % rhenium and 10 weight % rhenium. The activity is drastically decreased even larger amount of the rhenium species. This is a result of the gamma spectra of these catalysts. But in the case of the lower loading amount of catalyst, this peak was not observed, but the higher loading amount of catalyst shows a very clear peak, which is assigned to the rhenium oxygen rhenium vibration. Therefore, we are thinking that the radium for the samples with a large loading radium amount, suggesting that the inactive radium species is polymerized species, such as dimer and trimer and so on. On the other hand, the isolated monomer species is so active. This is a model structures. The monomeric radium species is active, but the bridging radium polymerized species show the no activities. Another important point, the dependence of the loading amount radium here indicates that the reached limit is not active, and the radium on celia is active in the DOTH space. According to the kinetic analysis, for example, the zero reaction order with respect to the hydrogen, and almost zero reaction order with respect to the concentration of the divols, we propose that this kind of recycle is proposed. And the very important point is that radium plus species is stabilized on celia surfaces. The separation, which is connected to the separation of the further reduction of the radium species, for example, 2 plus, 3 plus, 0, and so on. At first, start with a radium 7 plus, but the radium 6 plus is formed by the reduction by reduction of the hydrogen spillover, as I mentioned later. The radium 4 plus is formed, and the diorite is formed, and then the elimination of the alkanes. This is a rate determining step. And another important point is that when palladium is used, the palladium shows very high catalytic activity of cis double hydrogenations. Therefore, the saturated product is a main product in this on this catalyst. In the case of the homogeneous catalyst, redox cycle is the radium 7 plus and radium 5 plus. On the other hand, in our case, the redox cycle is a little different, radium 4 plus and radium 6 plus. We are thinking that this is one electron reductant, for example, the spillover hydrogen. Usually, in the case of the homogeneous catalyst, 2 electron reductant are used, for example, the secondary alcohols and the propylene phosphine. Therefore, starting state is the radium 7 plus and is reduced to the radium 5 plus. And the DODH reaction proceed, radium 5 plus is back to the radium 7 plus. On the other hand, in the case of the heterogeneous catalyst, hydrogen is activated on the metal surfaces and transport to the radium species. Therefore, the radium 7 plus is reduced to the radium 5 plus, 4 plus, 6 plus, 5 plus, 4 plus. The important point is the celia is very important load, has an important load on separation of the further reactions. Radium 4 plus is stabilized on the radium surfaces, celia surfaces, and this is this site is completed the radium 6 plus and the radium 4 plus for the DODH reactions. The disadvantage of palladium is CC double bond is hydrogenated to the CC single bond. Therefore, we use gold for separation of the CC double bond. For example, the glycerol can be converted to the allyl alcohol in a very high yield, and the erythritol can be converted one three with the ions, one for hydroxyetone can be provided with the hydrogen and so on. Important point is that for the suppression of the cis double bond halogenation, we use a very large size of the code. For example, I'm sorry I did not show the characterization results, but it is concluded that the size of the gold is 12. 12 nanometer means so large, and the size is almost the same as a serious apple. Therefore, the structure of the catalyst is like this. For example, the one serial particles have 60 radium atoms. But the important point is that number of the gold particle is so limited. For example, the number of ratio is 1 to 3,000. Therefore, the number of gold particles is so limited, but the almost all the venue species can be active. Therefore, we are thinking that the hydrogen can be diffused to the almost all the venue species by hydrogen spillover like this. The number of gold particles gives the hydrogen species almost all the particles. The distance, large distance can be achieved from a limited gold particles. And the hydrogen species can supply almost all the living species or celia, which can be interpreted by spillover phenomena, hydrogen spillover, hydrogen spillover of the gold celia catalyst. Generally speaking, hydrogen spillover is considered as a gas-solid interface in the usual case. But in our case, the hydrogen spillover, the liquid-solid interface may be important, and solvent molecules may have some roles in the spillover effect. In order to investigate the effect of hydrogen spillover, we use physical mixed catalyst. In our case, the physically mixed catalyst is so simple. The one was break reactors, two different catalysts in put into the same autoclave separately. The very simple, and the solutions, the powder is mixed with a magnetic star. In this case, rhenium celia show the very low reactivities. Rhenium gold celia has some activities. In this case, the gold size of gold is 12 nanometers. 3 nanometer gold gives a higher activity, but in this case, the selectivity is not so high. Hydrogenated products, one propanols also Chris Halder also found that the small size of the bone showed very high catalytic activity. Therefore, these kind of the products are observed. And in the case of 12 nanometers, rhenium gold celia plus celia, and the rhenium celia plus gold celia catalyst. We are thinking that these activities are almost the same. Therefore, the rhenium gold celia activity is similar to the case of the physically mixed catalyst. Close contact between the rhenium and gold is not necessary. So that large gold celia is connected to the lower catalytic activity. Therefore, we survey another method for candidates. silver is a very good component for these reactions. For this here, copper, palladium, ruthenium, iridium, and so on. The silver shows a very high conversion and high selectivity to the ones with the ion. The activity is higher than the case of the gold. This is the results, characterization results of the rhenium gold serial catalyst. As you can see, the large size of the gold is observed here, but the some dispersed gold, silver was also observed. On the other hand, the XRD Ipsos analysis gives silver cage. Ipsos analysis gives coordination number of the silver bond, the 8.5 and 7.7, the fresh catalyst and the used catalyst. Aggregated gold particles were observed, and the coordination of gold and silver is not so high, which is much smaller than the case of the silver foil. Well, and this suggests that the existence of the well-dispersed species was suggested. The coordination number of the gold was almost changed, even the catalytic use. Therefore, on this rhenium silver serial catalyst, have both smaller silver particles and the large silver particles. But this is a comparison between the silver and the gold, gold 12 nanometers. This is a reaction time. We would like to compare the selectivity at the similar version levels. Therefore, the reaction time is adjusted. The selectivity of the products very, very similar. On the other hand, the reactivity is so different. Silver catalyst is clearly, activity of the silver catalyst is clearly higher than gold catalyst. Another important point is that low ability of CC bond hydrogenation in the case of the silver, and smaller silver particles also have a impact in CC bond hydrogenation. On the other hand, the high hydrogen activation ability is achieved by using the silver particles. And this is a simple kinetic studies. Reaction rate as a function of the hydrogen pressures. The reaction order with respect to the hydrogen pressure is almost zero. But this shows the high activation ability of silver. This is the result of the time course of the reaction, erythritol reaction using the rhenium silver serial catalyst. This is a result of the 1,4-dioxane solvent, and this result solvent-free conditions. In both cases, the very, very high yield of the 1,3 with the diamond achieved in both reactions. Important point is that if the conversion is almost 100%, in such cases, the hydrogenation of the CC double bond is also proceed, and the proteins and the normal retainers detected. Here, I would like to compare these catalysts with the results on the rhenium gold serial catalyst. Small gold particles have the high hydrogen activation ability, but the CC double bond hydrogenation activity is also high. Therefore, the product distribution is completely different. The 1,3-butadiene yield is here and here. In the silver case, the very high yield of the mass butadiene observed, but the renewable cereal can give very low high 1,4,1,3 butadiene yield. The conversion is similar behavior like this. Next, I would like to talk about the regeneration of the renewable cereal catalyst. In the case of the only the drying procedures, catalysts debated this, but the calcination is inside procedures. The catalyst can easily regenerate. We are thinking that the monomeric radio species is active, but the two kinds of the reasons are present in the deactivation. One is the unsaturated product is a main product in its reactions. Therefore, the carbonaceous materials are positive catalyst. And another important aspect of the deactivation is that Lenium monomeric species is aggregated to some extent. In such cases, the Lenium monomeric species is polymerized and the activation is lost due to the polymerizations. But if you have signed the catalyst, probably the dispersion of the species, therefore this catalyst is regenerate. And okay, the final topic is physical mixture of the rhenium ceria plus the nickel ceria catalyst. In the case of the nickel metals, full loaded catalyst is show very low activity. On the other hand, physically mixed catalyst show a very high activity. Unfortunately, this catalyst is difficult to regenerate. One reason is the interaction between the nickel metal and the rhenium species. For example, the reduced rhenium nickel catalyst, in this case, the valence of rhenium is so low, much lower than the usual case, physically mixed case. Low activity of this catalyst can be due to the over-reduction of the rhenium species. And high activity of the physically mixed catalyst can be due to the maintenance of the highly balanced species. In the same on the same rhodium cerium catalyst, cerium particles, the rhenium and nickel is co-present, and in such cases the interaction is so strong. Therefore, the nickel alloy, nickel rhenium alloy, or the nickel metal particles modified the rhenium with high lower valence rhenium species form during the reactions. This is a very contrast. In the case of the nickel, the regeneration is not easy, but in this case, one of the differences is that nickel catalyst has a larger molar ratio of the nickel to rhenium. Okay, this catalyst can be applied to the various kinds of the deonator. Like this, for example, xylitol is converted to the 1-pentanol and the 3-pentanol in high yield. Okay, let me summarize my thoughts. Small silver particles can have high hydrogen activation ability and very low activity in the cis-hydrogenation which is a little different from the whole case. And it is better to put nickel uh, away from the radium species. The physical mixture catalyst is so good. The hydrogen spillover plays a crucial role on the reduction of the radium species of celia and even in the decayed solid interface. Finally, I would like to express my thanks to all members of my laboratory and the financial support from these funding agency and Japanese companies. Thank you very much for your attention.
Questions?
Thank you for your presentation. My name is Kingsley from University of Kansas. So in particular, you use the word on dioxin as soil. Why did you use this? Why not other types of solvents? Then, in the course of using these solvents, you had one time you had a TOF of 280, then you used cerium rhodium complex. So did you have anything like a solvent cyclization? Because we didn't see that you tried other types of solvents.
Usually, solvent is very convenient for the experiments. Therefore, we demonstrated under the solvent-less conditions. Of course, the solvent is not necessary for our reactions. But for example, erythritol can be converted to the 1,4-butadiene, 1,3-butadienes. In such cases, after the reactions, all the product is gas phase. Therefore, generally we use a solvent, but the solvent is not so essential in our experiments, in our reaction systems.
In the interest of time, we'll close the session now and thank Professor Tomishige.